class on fundamentals of electrical engineering. We are moving to the last session in this portion wherein we are discussing Fourier transforms, and that too as a part of signals assistance. Moreover, there's a little more of explanation here. We'll be looking at sampling as well. In fact, we have been looking at sampling as a part of most of the topics, but now we will be looking at a little bit of sampling as well in the coming slides. So let's move to the first problem directly. This is still a Fourier transform problem. The Fourier transform for continuous time signal xt is given by x omega is equal to 1 by omega plus j omega whole square. Immediately, what should come to your mind is the Fourier transform of Fourier transform in relation to Laplace transform. This is something like 1 by s plus 10 whole square. Okay, so because in Fourier we don't have sigma, so it's almost identical. In that sense, it is identical. If that be the case, then it's very simple to find out the Fourier inverse. Okay, because Laplace inverse comes to our help in this context. So, and this is applicable, that is x omega as equal to 1 by 10 plus j omega whole square is applicable so long as for the entire frequency plane, that is minus infinity to plus infinity of omega. Moreover, j is explained as the square root of minus 1 and omega denotes frequency. Then the absolute value of natural logarithm of xt at t equal to 1 is what? Okay, so is what is asked. Okay, so yeah, so now of course we can as was said earlier, the Fourier inverse is very clear. It's the same as equal to t into e raised to minus 10t. Now we have to take the natural logarithm and at the same time take the value at t equal to 1 and then find the absolute value. So let's go to the first step. Taking the natural logarithm, we find that it's the same as equal to ln t. T is replaced by 1, so it is ln 1, and then we are having plus minus 10t into ln e, which is ln e becomes equal to 1, and minus 10t where t is the same as equal to 1. Okay, so we have and so the absolute value is now ln 1, which is equal to 0, minus 10 into 1, so absolute value is equal to 10. So the first answer itself happens to be true, that is a equal to 10. A tells you that this value is equal to 10. Okay, so we don't look at the other answers because there is only a unique answer here. And in most cases, we notice that in the gate examination, the first answer, if there is some kind of computation required, the first answer or the second is normally true. Okay, let's move to the next one. Here we are having a different situation. The value of the integral 2 of something that is similar to a sinc function, that is sine 2 pi t by pi t. Okay, it's integrated from between minus infinity to plus infinity. Okay, so this is the same as equal to thinking in terms of sine 2 pi t by 2 pi t. Okay, and then there's a multiplication by 2 as well to get that 2 pi t. If that is the case, then this is the same as getting an area of a rectangular function which has value equal to 1. Okay, when you integrate 2 into sine 2 pi t by 2 pi t dt with respect to time from between minus infinity to plus infinity, you get 1. Okay, so multiplied by 2 gives you the answer, and from amongst the 4 options given, we can easily select the 4th option as the correct answer, that is 2. Okay. Now we have a sampling question wherein we have x1 omega which extends from minus beta b1 to plus b1. It's a staircase kind of appearance it has a staircase kind of appearance for the Fourier transform. And there is also another triangular kind of Fourier transform for another function x2t, okay, which gets x2 omega, which again ranges between minus beta 2 and b1. Let x1t is have a Fourier transform of x1 omega, and x2t Fourier transform is equal to x2 omega. The two signals whose Fourier transforms are as shown in the figure below. In the figure, ht is equal to e raised to minus 2 absolute value of t denotes the impulse response. Okay, so now we have we are shown also that x1 and x2t are multiplied. Okay, which is always telling us about the frequency. Okay, when you multiply them together, and then you are having the impulse response ht is equal to e raised to minus 2 beta t. Okay, and for the system, okay, and that gives you the output for the system shown above. The minimum sampling rate required to sample yt so that yt can be uniquely reconstructed from its samples, because the signals are getting multiplied together. Both the frequencies need to be added together, as we have seen earlier. So we have beta 1 plus beta 2 to get the sampling frequency, of course, multiplied by 2. Okay, so it's that the band limitation in both x1t as also x2t can be taken into consideration. So so obviously the sampling frequency is going to be 2 into beta 1 plus beta 2, where beta 1 and beta 2 are given in radians per second. Okay, so this answer is also in radians per second. Okay, so most of the problems are in this genre now. The output yt, okay, again we have another similar situation wherein xt and which has a Fourier transform as given by x omega is getting multiplied by cos 1000 pi t. We have seen a similar problem, and x omega has a frequency from between minus 1000 pi t to minus 1000 pi to 1000 plus 1000 pi. Okay, and then we are having ht, that is the impulse response after the multiplication. The impulse response is given by sine 1500 pi t by pi t. Okay, again we are having it's very clear that we are having a sort of a sinc function there. Okay, as the output. Okay, and then the question is, the output yt of the following system is to be sampled so as to reconstruct it from its samples uniquely. The required minimum sampling rate, without doubt, we see that sine 1500 pi t has omega is given by 1500 pi. So if you divide it by 2 pi to get frequency, it's equal to 750. And then this has to be multiplied by 2 according to the sampling law or the Nyquist criterion. And so we are having, or Shannon's law, we see that the sampling rate should be 1500 samples per second. Okay, so option A, no. Option B is 15 samples per second. So that's what we opt for, just from the output. Okay, and then let's move to the fifth problem. For the signal ft is equal to 3 sine 8 pi t plus 6 sine 12 pi t plus sine 14 pi t, the minimum sampling frequency in hertz satisfying the Nyquist criterion. Okay, so we have the signal ft which has the largest frequency as given by 14 pi, or 14 pi divided by 2, that's equal to 7 hertz. Okay, so this 7 hertz is going to be the band limitation associated with this. So multiplied by 2, so 14 is going to be the sampling frequency according to Nyquist criterion. Okay, satisfying Nyquist criterion, so minimum frequency rather. Let's move to the sixth problem. A sinusoid xt of unknown frequency is sampled by an impulse train of period 20 milliseconds. So if a sinusoid xt of unknown frequency is sampled by an impulse train of period 20 milliseconds, the sampling frequency is given by sampling period is given by sampling period is given. So sampling frequency is given by 1 by 20 milliseconds, which is equal to 50 hertz. Okay, the normal frequency. The resulting sample train is next applied to an ideal low-pass filter. Now, this sample signal is going to a low-pass filter with a cutoff frequency of 25 Hz on one side. The filtered output is seen to be a sinusoid of frequency 20 Hz. This means that xt has a frequency. Very simple, because we already have a filter there. What happens is that what comes out is the same as equal to the frequency of the frequency of this signal. Then again you have 50 hertz. So plus 50 hertz and minus 50 hertz, or minus 50 hertz should give us 20 hertz as the output of the signal. So obviously 50 plus 20 or 50 minus 20 will give you the frequency of the sinusoid or the input that is being sampled at 50 hertz. Okay, so we have 10 hertz, 60 hertz and 30 hertz. So that's one of the answers. Okay, and which is true, and 90 hertz. So only 30 hertz happens to be 50 minus 20. 50 is the sampling frequency, and the 30 happens to be the frequency of the sinusoid which is being sampled. So 50 minus 30 gives you 20 hertz as the output of the sinusoid. Okay. Yeah, so that's also very, I suppose, just a direct application of the Nyquist criterion. Moving on to the sixth problem, again, the Nyquist criterion based problem. A band limiter signal with a maximum frequency of 5 kilohertz is to be sampled. So, for it to be sampled appropriately for reconstruction, twice this frequency, that is 10 kilohertz, is the minimum frequency required. Okay? According to the sampling theorem, the sampling frequency in kilohertz, which is not valid, is okay. So all options other than A happen to be valid, because more than 10 kilohertz was required for sampling it appropriately. But here we have only in option A, we have less than 10 kilohertz, that is 5 kilohertz. Okay? So we opt for option A here as not being valid. Okay? The frequency spectrum of a signal is shown in the figure. That's in the 8th problem. What do we have here? We see the spectrum as a triangular one, and it lasts between -1 to 1 as for frequency in kilohertz. Okay, and we are told that the frequency spectrum of a signal is shown in the figure if this is ideally sampled at intervals of 1 millisecond. So 1 milliseconds means 1 by 10 raised to -3 or 1 kilohertz, which is very small compared to what is required for sampling this. It is the band limitation tells us that you require 2 kilohertz at least, and this is only half. So what happens is that it will always see the same value, which is equal to a particular magnitude, and that is what is going to be the output. Okay, and then what the question is, then the frequency spectrum of the sample signal will be just like getting a continuous. The spectrum will be continuous. It will be something like an all pass. Okay, so we look at the 4 options A, B, C, D. Though it appears as though B is right because of the folding of the frequency, but that's not right. We get what is called as nothing is retrieved because the frequency is very small, and so what the sampling the frequency is very small. So we have a constant value emerging as the output. Okay, so that's all here. So we were mostly talking about Nyquist criterion. We were talking about the frequencies. We also talked about when signals are multiplied together as to how the frequencies as to how both the frequencies need to be taken into consideration when sampling. We also looked at one fundamental understanding of Fourier transform and another of the integral of a sinc function. Okay, of course, after seeing to it that it follows a particular pattern. Okay, so these were some of the items that we had looked through in this session, and with that we will be going into control systems in the next as the next module. Thank you.